Okay, so let's continue. Well, polarization is one property of these electromagnetic waves, but we had already seen that in general for electromagnetic fields, whether it's a wave or not, independent of that, we know that we can talk about the energy density of the electromagnetic field, the momentum density of the electromagnetic field, etc. So let's say we have these waves. Now let's see what about the electric field and the energy density and the momentum density. Now if you remember the energy density, do you remember what's the form of the energy density? Again, for simplicity, let's stick with the linear polarization. And for the case of linear polarization, we know that the physical electric field is nothing but E0 times cosine kz minus omega t, and B field is B0 times cosine kz minus omega t. And if you just put in over there, the energy density is 1/2 epsilon 0 E0 squared plus 1/2 mu 0 B0 squared times cosine squared kz minus omega t. Well, we also know a relation between the magnitudes of B0 and E0. C or 1/C? 1/C or C? Well, you see, units should always match. And always keep in mind that the force is QE plus V cross P. The unit of E is always some speed times the unit of P. So you can just, if you know that it is C, but you are not sure whether it's C squared or C or 1/C or 1/C squared, just check the units. They will help you remember what the coefficient is. So E0 is C times B0. Or instead of B0, since we are expressing everything in terms of the electric field, like the polarization is defined as the direction of the electric field, we can do the same thing over here. B0 is 1/C times E0. So the energy density is 1/2 epsilon 0 E0 squared plus 1/2 mu 0 1/C squared E0 squared times cosine squared kz minus omega t. Well, 1/C squared is nothing but mu 0 epsilon 0 that we had already derived. So if you just put it over here, mu zeros will just cancel. So here we would have just mu 0 1/mu 0 times 1/C squared is just epsilon 0. So we have 1/2 epsilon 0 E0 squared. And keep in mind, this is the energy density stored in the electric component. This is the energy stored in the magnetic component. It just turns out to be that they store the same amount of energy density. Well, you see, most of the time, for example, for light. The wavelength is very short, so k is very large. So this, in a very small distance, there will be many oscillations. Similarly, omega is large, of the order of 10 to the power 6 hertz or so. So in a very small amount of time, it will make many oscillations. So for as long as you don't have specialized equipment to measure such small variation, such fast variations, you will not be really measuring the energy density. But what you can measure is the average energy density, which is defined as 1 over T from 0 to T of U. It depends on R and T. Yeah, it's the time average. So you are measuring the energy flow over here. As time passes, this electromagnetic wave is moving through that point. And during that time, the energy density also oscillates very fast, so your device will just measure the average value at that point. And in this case, the average in a wave just turns out to be 1 over 2 epsilon 0 E0 squared. Well, basically because these are just constants, and the average of cosine squared is just 1 over 2. So this is our energy density. Now let's look at the momentum density, or the Poynting vector, energy flow, before that one. Do you remember the expression of the Poynting vector? 1 over mu 0 E cross B. And keep in mind that this is our E, this is B, this is K. So what is the direction of E cross B? It's in the K hat direction. What is the magnitude? They are orthogonal to each other, so the angle between them is just 90 degrees. Sine of that angle is just 1. So this is the Poynting vector. Now let's put in the E and the B fields. E0 times B0 times cosine squared kz minus omega t in the K direction. Again, B0 is just E0 over C. So S is 1 over mu 0 C times E0 squared cosine squared kz minus omega t in the K direction, or 1 over mu 0 C E0 vector squared cosine squared kz minus omega t in the K direction. Well, we can write this in terms of the energy density. You see, energy density was mu 0 C 1 over, there's no 2, epsilon 0 E0 squared cosine squared kz minus omega t in the K direction. This is our energy density. Well, I need to divide by this epsilon 0. 1 over epsilon 0. This is equal to, well, I have 1 over epsilon 0 times mu 0. Remember, that is nothing but C squared over C times U in the K direction. This is equal to U times C in the K direction. Well, this also makes sense. Remember when we were discussing about the current density was nothing but the charge density multiplied by the velocity of the charges. Poynting vector, if you remember, we said that it is the energy current. Energy current should be just the energy density multiplied by the velocity. This is the velocity vector. The wave is moving with the speed c in the k hat direction. So this is the velocity vector of the electromagnetic field, and this is the energy density. So this also is consistent with our interpretation of S as the energy flow.
E0 vector squared or just E vector squared?
Well, that is E0 because E vector contains this cosine part. Since I separated the cosine part, what remains is E0. Is E0 magnitude squared or E0 vector squared, they are the same thing. And if you want this E0 squared multiplied by the cosine squared, this product is just E squared.
I thought that they defined the E0 as a scalar in the last
E0.
one.
This one. This is equal to this one. Well, you see, this is my definition of the electric field in this lecture. These ones. In this example that we discussed in the last lecture, to be consistent with my other notation, I should have inserted a 1 over square root of 2. Meaning the magnitude of, to make sure that E0 is the magnitude of the electric field. But that's a special example. Now I'm continuing with this notation, with this convention. This is my electric and magnetic fields.
For mean value of U, is there any relation between this formula and the formula in quantum physics, like integral of psi star?
Well, of course, you can find many relationships, but that's the question of quantum mechanics. So in that course, ask that and see.
Birim olarak tamam hani K vektörünün direction'ında ama büyüklük olarak K vektörüyle hani ilişkisi ne bulabiliriz? Bu pointing vektörünün.
If you like, but I mean, it's basically the same thing. But you see, the thing is, the K vector can have any value. And if you look at the energy density that we derived over here, energy density doesn't depend on K. Well, it depends through that cosine. At least the average doesn't depend on K. You can have an average energy density, whatever value you like, independent of the value of K. So it doesn't really make sense to relate the energy density with the magnitude of K. K hat is the unit vector. K is the wave vector. K need not be a unit vector. The direction of, I mean, you see, the 1 over K, now, these waves, what we are talking about, plane waves, let's say this is my K vector. There's these perpendicular planes. All the points on these perpendicular planes, they have the same K dot R. Because K dot R doesn't depend on the component of R perpendicular to K. So all these points have the same K, this plane has the same value of K dot R. Hence, at a given time, they all have the same value of cosine K R minus omega t. They all have the same electric and magnetic field. This point, a different point, all those points on this plane again have the same value of the E and the B field. That's why they are called plane waves. And what was your question? Okay, so the K and the magnitude of K, you see, we have these planes and it's moving in that direction. So the wave doesn't change in this plane, it only changes in one direction. So in that direction, you can talk about the wavelength. And K depends on the wavelength. K is just 2 pi over lambda. K is proportional to 1 over the wavelength. You either talk about K, which fixes the wavelength, or you talk about the wavelength, which fixes K, the magnitude of K. In fact, at every point whether you talk about plane waves or arbitrary waves, you can, at every point, there's a direction of propagation, and you can talk about the wavelength in that direction. And the magnitude of k at that point will be inversely proportional to the wavelength in that direction. Well, k vector is not a number. That's why in 3 dimensions we usually call it the wave vector. But in 1 dimension it is the wave number. Now let's talk about the momentum density. So do you remember the definition of momentum density? It is mu 0 epsilon 0 s. Well, mu 0 epsilon 0 is 1 over c squared. S, we had just seen that it is energy density times c in the k direction. So it is u over c. This is the momentum density. Well, u is the energy density. Now keep in mind Einstein's E is equal to mc squared. Okay, the electromagnetic wave doesn't have a mass, but it has an energy. You can somehow talk about some kind of an effective mass, which will be E over c squared. Or if you want to talk about the mass density, this is the mass density, not the charge density, although we are using this rule for both of them. This will be the energy density divided by c squared. Now, if you would like to talk about some momentum density, should be equal to rho effective times the velocity. Well, naively, we could have expected such a relation. And if you go back to our previous notes when we were discussing the momentum density, we were saying that one would expect such a relationship. The momentum density should be some kind of an effective mass density times velocity. Well, in our case, the effective mass density would be the energy density, which is u, divided by c squared. This is the speed of the electromagnetic waves. The velocity is c in the k hat direction. They cancel. So you recover exactly this relation.
Hocam bu H ile ilişkilendirilebilir mi? Toplam.
No. That's quantum mechanics. Quantum mechanics, to start with, you have new assumptions that are verified experimentally. H comes from those assumptions. Quantum mechanics, you cannot derive it from electromagnetism. You cannot derive it from anything else. That's your fundamental law. Of course, as far as we know. Any questions?
Hocam ben kafamı
They are different things. You say, that, for example, your name is Serjan. There are many Serjans around, right? They are all called the same name, but they are not you. In a sense, you see, polarization, so where does the name come from? Poles, you have two of them. If you have two things, then you can form a vector. You talk about the polarization of vectors. Well, the charges, they move in two different directions. So that is the polarization. You can even talk about the polarization of the society. Basically, at least two different sides.
You obtain some continuity equation in free space. That's the in theory is possible.
Well, what do we know? You mean which, for example, we talked about the. Let's see. In this case, do we have mechanical energy? Mechanical energy? No, we don't have mechanical energy. We only have electromagnetic energy. So the conservation of energy in this case will be du by dt plus the divergence of S should be equal to 0. This is our continuity equation. In this case, because there is no mechanical energy. Well, if there is mechanical energy, we just need to add the mechanical part over here. So what is U? We had said that U is equal to epsilon 0 E0 squared cosine kz minus omega t. S is equal to UC in the k hat direction. Let's calculate the divergence of S. S depends on K, on R and T, sorry. It depends on R and T only through U, which depends on Kz minus omega T. Okay, do you agree? So let's take the derivative of S with respect to X. What is that derivative? 0. What about the derivative of S with respect to Y? 0. Derivative of S with respect to Z. It's derivative of U with respect to all of its arguments. C times K hat is Z times K, sorry, times K times C in the Z hat direction. Well, this is the U. It only depends on Z and T. In this particular example. Well, the divergence of S. This is dsx by del x plus del sy by del y plus del sz by del z. This is 0. This is 0. This is equal to u prime kz minus omega t times kc. Now let's look at del u by del t. U is the first line on the screen. This is equal to the derivative of U with respect to all its arguments times minus omega. This is equal to minus u prime kz minus omega t, but omega is nothing but k times c. So du by dt in this particular example is equal to minus the divergence of S. Now, our derivation of this relation before didn't make any assumption on the form of the electric and magnetic fields. Whatever the shape, whatever the source, whatever the behavior of the electric and magnetic fields, they have to satisfy this relation. U being the energy density stored in the mechanical component and also the electromagnetic component. So here we have a particular case. So if we did everything correct, if our calculations were correct, they had to satisfy this relation, and we had just shown explicitly that they do satisfy that continuity relation.
What is u prime? U prime derivative u with respect to x, y, and z?
Or instead of x, let's call it alpha, I don't know. Because you see, u depends on only the component, only the combination kz minus omega t. I can treat u as a function of a single argument. It doesn't depend on z and t separately. It depends only on that combination, and u prime is its derivative with respect to that combination.
Hocam bu continuity equation yani bize dalganın sürekli olduğunu diyorsun.
No, this equation we derive as a conservation of energy. This relation tells me that energy is conserved. Well, we already derived it proving that energy is conserved even if when we have electromagnetic interactions in the system, as long as we identify the energy density in the electromagnetic field. In this particular example, we have a wave, and in this wave, we see that energy is conserved also. This is just a special case of our derivation in the first weeks.
Conservation of continuity anlayışı.
Continuity means conservation. You see, what continuity tells me is that if you just integrate this over a volume, the change of this quantity in that volume is due to something that is going out through the surface of that volume.
Mekanik enerjiyi de yani niye düşünüyoruz?
Well, because our solutions of electromagnetic fields are valid in case of vacuum.
Ama sonuçta o elektromanyetik dalgada hani bir yerden geldi. Hani
Sure, but that is somewhere out of my volume. I cannot use, these expressions of the Poynting vector, the momentum density, energy density are valid only in this volume where there are no charges. And what we had seen, since we had shown that it satisfies this continuity equation, what this demonstrates explicitly is that within this volume, energy is conserved. We already have the more general proof that energy is conserved everywhere. But since our solution is valid only in this volume, the only thing we can show explicitly using these solutions is what happens within these volumes, where there are no charges. The only thing there is the electromagnetic field. So that's why there is no mechanical component to the energy in this volume.
Sadece dalgaları bile düşünsek o da kendi içinde tutarlı.
Sure. It should be. Our derivation of conservation was quite general. We didn't make any assumption about the kind of field we have, about its source, origins, its behavior, whether it's a wave or not. Whether there are charges or not, it is valid in every circumstances.
Peki kaybedilen enerji nereye gidiyor? Momentum mu oluyor? Yani
Well, what does it mean that the energy becomes
şimdi,
momentum?
du bölü dt işte ikisi de hani birisi zaten enerji density, diğeri de enerji. Yani hani
S is not the energy, it's the energy flow. U is energy density, S is energy current.
kaybedilen enerji o zaman.
But I'm talking about my volume. In this volume, if the energy, or at this point, in this volume, if the total energy in this volume, the total energy meaning the integral of U, if it is changing, it tells me that it just moves out of the surface. Now, what happens after the surface? Well, I have to look what is out of the surface. Maybe it's vacuum, so it keeps moving. Maybe there are charges over there, so it is absorbed by the charges, gives energy to the charges gain momentum. The only thing I know is that if the energy in this volume is changing, it is because energy is flowing through my surface.
Hocam eğer bu sıfıra eşit olmasaydı herhangi bir sayıya, bir şeye eşit.
Then there is no conservation.
O zaman bir şeyler ısıya mı dönüşüyor?
You see, saying that it is changing into heat is claiming that it should be conserved. It is going somewhere else. So that is conservation. If it was equal to something else, it can just disappear. It can just increase. Then it would tell me that it is not conserved. It can just appear out of the blue.
Peki böyle bir sonuç fiziksel olur mu?
But energy, we strongly believe that energy is conserved. But who knows? We have experimental limits, which says that at least on Earth, energy is conserved. We would rather stick with energy conservation than claim that there's something energy is violated. You see, most of our measurements, for example, if you know the history of the discovery of the neutrino, experimentally there was energy non-conservation. So either we would expect that there was energy non-conservation, or we would agree that there's something that we are not observing. So that is the way we proceeded. Rather than giving away energy conservation, we hypothesized that there was something else we were not observing. Now, later on, we did observe it. When you see classical mechanics, or you're probably seeing classical mechanics, energy conservation is mainly related with the fact that the laws of nature should be independent of time. As long as laws of nature are independent of time, meaning that those laws that were valid now should be valid, 1,000 years from now, there is a scalar quantity that will be conserved, and that quantity is what we call energy. Okay, so that is basically what we will discuss about the waves in vacuum. Rarely we have waves in vacuum, we have the atmosphere, to say the least. So the next thing we will discuss will be waves in medium. So first, let's try to remember what are the Maxwell's equations in medium. This rho, I will just drop the index free. So this is just rho. Del dot B curl of E
Minus dB.
and curl of H
C D mi?
Now, again, for simplicity, we will be dealing with linear media. For linear media, and B Hı?
1/mu H.
Do you agree?
Mu zero, epsilon zero desek bir şey değişir. Hocam,
Well, in vacuum, epsilon is equal to epsilon 0, and mu is equal to mu 0.
B is equal to mu.
Well, let's see. Let's look at in vacuum. In vacuum, curl of B was mu 0 J. Yep. Plus del E by mu 0 epsilon 0, del E by del T. Divide by mu 0. This cancels, this cancels. This is what we call H in vacuum. So it's mu times H. Or H is equal to B over mu 0, mu. Now, let's put these D and H back into the Maxwell's equation. Let's assume we have a homogeneous media. So del dot E is equal to rho over epsilon. Del dot B is equal to 0. Curl of E is equal to minus del B by del T. Curl of B is equal to mu J plus mu epsilon del E by del T. Mathematically speaking, they're identical to our Maxwell's equations in vacuum. So we don't need to do all those derivations again. So just replace epsilon 0 by epsilon and mu 0 by mu, and all our previous results will still be valid here. All the conservation laws will still be valid because if you remember, we derive the conservation laws using the Maxwell's equations with this identification. All the derivations about the wave vectors will still be exactly the same. Of course, we should keep in mind now that the velocity of electromagnetic waves, the velocity squared will be 1 over epsilon times mu, not epsilon 0 times mu 0, which we can write as epsilon 0 mu 0 divided by epsilon mu times 1 over times c squared, or V is equal to c over n, n being square root of epsilon mu over epsilon 0 mu 0. Now we will see that this is called the index of refraction. We will see later on why it is related to the refraction. So basically, electromagnetic waves, when they enter a medium, they will slow down. They will not move at the speed of light c. They will just slow down. Most of the time, the mu is very close to mu 0. The deviations will be very small most of the time. And the deviation between mu and mu 0 is at the order of 10 to the power minus 4. If we are not talking about ferromagnetic materials, so most of the time this will be just epsilon over epsilon 0. So the polarizability of a medium will determine the speed of light in the medium.
hocam peki medium homojen olması
So suppose we have these two different media. Epsilon 1, mu 1, epsilon 2, mu 2. This is no longer homogeneous. So now what will happen? So let's say we will study several cases. The simplest case that we will basically study will be when we shine light straight perpendicularly. This is our k vector. Let's say this is our E0. And this is our B0 out of the screen. So just imagine light, a glass. So there's glass. You shine some light, some electromagnetic radiation. It's moving in K. Well, observation tells us that some of it will be reflected backwards. So this will have some minus K vector. Let's say this is our E0 prime. What will be the direction of the B0 out of the screen into the screen? Into the screen. This is B0 prime. And again, observation tells us that some of the light that we shine on a glass, it just passes through. K prime, E0, well, let's say K double prime, E0 double prime, and B0 double prime. Now let me choose some axis. This is my z-axis. Let's say this is x, this is y. So E0 is E0 in the x-hat direction. B0, this is B0 in the y-hat direction. E0 prime is some E0 prime in the x-hat. B0 prime is some B0 prime in the minus y hat. And E0 double prime, this is E0 double prime in the x hat. B0 double prime is B0 double prime in the y hat. Well, let's see. I know that I can choose the direction of E0 vector as my x direction, so I know that this number is positive. Well, I can choose the direction of B0 vector as B0, so I know that as the y-hat direction, so I know that this number is also positive. So by definition, these two numbers are positive. I don't really know whether E0 prime is positive or not. After reflection, maybe E0 points in the opposite direction. I don't really know. So this number E0 prime might be negative. But E0 prime and B0 prime, they are either both negative or both positive. Because E cross B should give me the direction of the K vector, which is pointing in the minus Z direction in that case. So both of them are either positive or both of them are negative, but I don't know which one. Similarly here, E0 double prime, there's no vector sign over here, and B0 double prime, those numbers, they can be positive or they can be negative, both of them. Now the question is, how do I determine them? So that will be our question for Friday. You see, the thing that we will be used, I strongly suggest you to review the concept of the continuity of the electric and magnetic fields across a surface. You see, on the left-hand side of my surface, the total electric field will be just the sum of these two. And the total magnetic field will be the sum of these two. On the right of the surface, the only electric field is this one, the magnetic field is this one. So basically, how does the electric field change as we cross a boundary in electrodynamics? So those will be the conditions which will allow me to determine this transmitted and reflected electric and magnetic fields. So how does the perpendicular component of the component of the electric field perpendicular to the surface change? Well, in this case, there is no perpendicular component. The perpendicular component is the same on the left and on the right. It's 0. How does the component parallel to the surface change as we cross a boundary? And similarly for the magnetic field, how do they change? Those conditions, those boundary conditions, will allow me to determine these ones in terms of our initial wave. And then we will be able to see how much of the wave will be transmitted, how much of it will be reflected back, etc. Now, any questions before you go? Review the derivations of the boundary conditions definitely before Friday. So see you on Wednesday.